Hello everyone. The first unit of Chem 1 is a review of basic chemistry concepts. In this week's lecture, we will focus on atoms, molecules, and the periodic table of elements.
Anything that exists in our world and beyond is matter. Matter is anything that occupies space and has mass. Even the period at the end of this sentence is considered matter. Matter can be as big as the universe or as small as an element. An element is the simplest unit of matter that has unique properties. When an element is broken down into smaller units, it loses these unique properties. The atom is the smallest unit of an element. Individual atoms also have unique properties. For simplicity, the terms atom and element are often used interchangeably. I'm sure you are already familiar with many elements. Elements are represented by letter symbols. The letters usually correspond to the first letter of the element's name. For example, the symbol for the element carbon is C. H is for hydrogen, O is for oxygen, N is for nitrogen, and S is for sulfur. Many elements are symbolized by one letter only, but other elements use two letters to avoid confusion with other elements that start with the same letter. For example, chlorine is symbolized by the capital letter C and small letter L to avoid confusion with carbon. For some elements, the symbol is derived from its Latin name. The letter K is the symbol for potassium and is derived from its Latin name kalium. Au is the symbol for gold and is derived from aurum. And Hg is the symbol for mercury, which is derived from mercurius supernatant.
The periodic table of elements lists the different elements into an organized non-random placement. All the elements that have been discovered and characterized so far are listed in the periodic table. There are some elements that have yet to be discovered, but their properties have already been predicted. The periodic table is organized according to the following. First is by atomic number. The atomic number of each element is always listed with the element. In our periodic table, the atomic number is written on the upper right-hand corner of the element box. The atomic number of iron is 26. Elements are arranged in increasing atomic number from left to right, first row to last row. Hydrogen has an atomic number of 1. It is the first element in the periodic table. Helium has an atomic number of 2. It is the second element in the periodic table. And so on and so forth until we reach 118, the largest atomic number. Each row in the periodic table corresponds to a period. Elements in the same period have the same number of electron shells. There are 7 periods in the periodic table. Each column corresponds to a group of elements. The atomic number plus electron shell gives elements in each group the same chemical and physical properties. There are 18 groups in the periodic table. The elements are also organized into large groups. Group 1 elements are called alkali metals. Group 2 elements are called alkaline metals. Groups 3 to 12 are transition metals. Groups 13 to 15 include other metals. Groups 13 to 16 include the metalloids. Groups 14 to 16 include the nonmetals. Note that the elements essential to organic chemistry are nonmetals. Group 17 elements are called halogens, and Group 18 elements are called noble gases. The noble gases are the most stable, least reactive elements in the periodic table. The lanthanoids and actinoids are transition metals, but they are placed in separate rows due to many unique properties. In a later module, we will discuss another important grouping called the SPDF blocks. The atom is the smallest unit of an element. It was originally thought that the atom could not be broken down into smaller units. However, we now know that atoms are composed of even smaller units called subatomic particles. They are protons, which carry a positive charge, neutrons, which have no charge, and electrons, which carry a negative charge. An element can exist in different forms depending on its number of electrons and neutrons, which can vary. Elements with different number of electrons are called ions. Elements with different number of neutrons are called isotopes. An element will always carry the same number of protons. That is why the number of protons is important to an element's identity. It is called its atomic number. For the sake of simplicity, in this lesson, we will consider an atom as equivalent to an element. The English scientist John Dalton was the first to propose a definition for the atom. His atomic theory is still the widely accepted description of the atom to this day. The atomic theory states that all matter is composed of atoms. Atoms of the same element are the same. Atoms of different elements are different. Atoms combine in whole number ratios to form compounds. The subatomic particles have a specific arrangement in an atom. The protons and neutrons can be found in the center of the atom. They form the nucleus of the atom. Electrons orbit around the nucleus in orbitals. Electrons, protons, and neutrons are actually made up of even smaller particles. They are called quarks, leptons, and bosons. Because atoms are so small, it is not possible to visualize it. So scientists have come up with several models to represent the atom. These models all share the same concept, that protons and neutrons make up the nucleus of the atom, and electrons spin around the nucleus. What is different about these models is just how electrons move around the nucleus. The quantum model proposed by Erwin Schrödinger in 1926 remains as the most widely accepted model of the atom. The most important information about the quantum model is that electrons do not move around the nucleus in a set path. Instead, they travel in clouds or orbitals where their exact position cannot be determined. The second tenet of the atomic theory states that the atoms that make up an element are unique to that element. Why is this so? Atoms that make up an element all have the same basic characteristic, the number of protons. Atoms that make up another element also have the same number of protons, but it is not the same number as our first element. This unique characteristic of an atom in an element makes it possible for us to correctly identify that element. That is why the number of protons of an atom is also the atomic number of the element. The periodic table of elements identifies each element by their atomic number. As mentioned earlier, elements are arranged in the periodic table according to increasing atomic number, from left to right. The atomic number is written as whole numbers next to or above the element name. Hydrogen has only one proton, so its atomic number is 1. Iron has 26 protons, so its atomic number is 26. In a stable state, the number of protons of an element is equal to its number of electrons. However, elements can gain or lose electrons. When this happens, the element exists as an ion. However, the atom remains the same element regardless of the number of electrons. How can we determine the number of neutrons in an atom? The number of neutrons is determined by subtracting the number of protons from the atomic mass. Let's take the case of iron as an example. To determine the number of neutrons of iron, we subtract the number of protons from its atomic mass. The atomic mass of iron is written here, 55.845. Subtracting the atomic number, 26, gives us 29.845. So, the number of neutrons of iron is 29.845. As mentioned earlier, an element becomes an ion when it gains or loses an electron. If an element gains an electron, it will have more electrons than protons. The extra electron gives the element a negative charge. If the atom loses an electron, it will have more protons than electrons. This gives the atom a positive charge. There are many elements that exist as ions. For example, elements in group 1 of the periodic table tend to lose one electron, giving them a positive charge. When lithium loses an electron, we can write this as lithium superscript plus. When Cl gains an electron, we can write this as Cl superscript minus. When an atom like magnesium loses 2 electrons, it becomes magnesium 2 plus. Most elements exist as a single atom, but some elements are stable when they exist as 2 or 3 atoms. Elements made up of 2 atoms are called diatomic molecules. Those made up of 3 atoms are called triatomic molecules. An example of a triatomic molecule is O3 or ozone, the gaseous molecule that is in our atmosphere that protects us from the harmful UV rays of the sun. Electrons play a very important role in how an atom reacts with other atoms. Specifically, the number of electrons in its outermost orbital or shell determines how and to what extent it can react with another atom. We will discuss valence shell electrons in the next module. Earlier, I mentioned that atoms can exist as diatomic molecules. What is a molecule? When 2 or more atoms combine, they form a molecule. Chemical bonding is an important step in the formation of molecules. Chemical bonding creates stable molecules that can exist independently. A molecule has chemical and physical properties that are different from its individual atoms. We can represent molecules using the molecular formula. When writing the molecular formula, we use the letter symbol of elements and indicate how many atoms of each element participate in the chemical bonding. So in these examples, the diatomic molecule oxygen is represented by the letter symbol O and the subscript 2, which indicates that there are 2 oxygen atoms in the molecule. The water molecule is made up of 2 atoms of hydrogen and 1 atom of oxygen. How many atoms of C, H, and O are present in the glucose molecule? How many atoms of C, H, and O are present in 1 molecule of ethanol? Many more molecules are formed between different elements. These molecules are referred to as compounds. The water molecule is a compound because it is made up of hydrogen and oxygen. Ammonia is another compound. It is made up of nitrogen and hydrogen atoms. The ozone that we mentioned earlier is a molecule, but not a compound because it is made up of the same atoms. We can say that all compounds are molecules, but not all molecules are compounds. Compounds can be categorized into two types, depending on what type of atoms bond together. A covalent compound is formed when a nonmetal element and a metalloid or another nonmetal element bonds together. An ionic compound is formed when a metal bonds with a nonmetal or another metal. Hydrogen tends to form bonds with nonmetals. When this happens, a covalent compound is formed. Here are some examples of covalent and ionic compounds. Methane is a gaseous compound from the bonding between carbon, a nonmetal, and 4 atoms of hydrogen. Table salt or sodium chloride and lithium fluoride are examples of ionic compounds. As mentioned earlier, molecules have physical and chemical properties that are different from its individual atoms. Take the case of sodium chloride. Sodium is a soft metal that explodes when reacted with water. Chlorine is a gas that is poisonous to most plants and animals. But sodium chloride, the molecule, is essential to life. In order for us to differentiate among the many combinations of atoms that form to become molecules or compounds, we need a system to name each compound that forms. How do we verbally differentiate between NO, NO2, and NO3? We can do this by following the system of chemical nomenclature. This system is a set of rules used to name compounds. Let's name the compound following a stepwise procedure. The first step is to identify all the elements present in the compound. Here we have an example, CO, CO2, and H2S. Starting with CO, CO is made up of carbon and oxygen. CO2 is also made up of carbon and oxygen. H2S is made up of hydrogen and sulfur. When naming compounds with more than one atom, we use the Latin prefixes to represent numbers. If there is only one atom of an element, we use the prefix mono. If there are 2 atoms, we use di. For 3 atoms, we use tri, and so on and so forth until we get to 10, where we use deca. The next step is to name the first element. So, for letter A, the first element is carbon. For letter B, the first element is carbon. For letter C, the first element is hydrogen. Since there are 2 hydrogen atoms, we add the prefix di. So we have dihydrogen. Next, we name the second element. Since there is only one oxygen, we attach the prefix mono. The stem of oxygen is ox. Then we add the suffix ide. This gives us monoxide. In chemical nomenclature, if the prefix ends with an O or A and the stem starts with an O, we drop the O or A in the prefix. So we say monoxide instead of monooxide. For the second molecule, we have two atoms of oxygen, so we use the prefix di. Add the stem ox, then add the suffix ide. This gives us dioxide. For the third molecule, we have one atom of sulfur, so we use the prefix mono. The stem of sulfur is sulf. Then we add the suffix ide. This gives us monosulfide. The last step is to combine the first and second name of the molecule. So in letter A, the first name is carbon. The second name is monoxide. So here we have the name of the compound, which is carbon monoxide. For the second compound, we have carbon plus dioxide. So we have carbon dioxide. The third molecule is dihydrogen plus monosulfide, which gives us dihydrogen monosulfide. Note, however, that dihydrogen monosulfide is not used as a name for H2S. Instead, we simply name it as hydrogen sulfide. This is because there are no other HS molecule that can be confused with H2S. So in the case of the first and second molecule, CO and CO2 exist, so we need a system to distinguish between the two. For H2S, however, there is no molecule that is HS and no molecule that is H3S, so we only have H2S. When this happens, we can omit the prefixes referring to the number, and we stick with just hydrogen and sulfide. So that's it for a lesson on atoms and molecules. You can replay this video as often as you like to have a better understanding of the topics covered. Your schedule for submitting the activity worksheet and quiz for Module 1 is September 11, 2020. Instructions for submission are written in your module. Thank you for listening.